funny name is Danish. So let's start with today's class. So no one has joined, but I will still start with the class, and I will first revise through the contents that we have covered, and then we will solve a couple of questions related to the contents of this week. So we started with the basic motivation behind the course, and we covered the conduction and solved few numericals related to the conduction phenomena, whereby we used this concept of resistance network in order to hello. Okay. So in week 1 we started with the basic motivation behind the course and then solved few numericals related to the conduction. So in conduction we use this resistance concept in order to solve the numericals, whereby we express the entire composite material, the resistance of the entire composite material, using a single resistance in whatever rate equation that we are using. For example, in conduction we have this. So yes, in conduction we use this Fourier's law, whereby the heat transfer rate is straight away proportional to the temperature gradient, and also is dependent on this K. So the same thing I can write it in terms of the driving force, that is delta T upon resistance. So we calculated this resistance using the resistance concept in week 1. Then we discussed few applications whereby this heat transfer can be useful. So whereby how can this course help you? So we looked into these applications. Then we studied this different mode of conduction, different mode of heat transfer, that is conduction, convection, and radiations. Then we solved the numericals. In week 2, we moved on to the radial systems and as well as this extended surface, that are fins. We looked into the basic derivations of the differential equations that governs these extended surfaces or fins, and then solved those differential equations corresponding to different boundary conditions. And then on the basis of that solutions, we solved the numericals related to it. So yes, in last class we covered with this we discussed this extended surfaces of varying cross section area. So basically we covered when the scenarios whereby we have multiple fins. Earlier in week 2 we only covered the dynamics, we only covered the equations related to the fins whereby we only had a single fin. But in practical scenario, we can have a combination of multiple fins. That is what we studied in this week 3. Then we covered this 2D plane wall. Then we moved on to the transient analysis, whereby the temperature of the given system can change with time. And for that we looked into various approximations such as lumped capacitance method. Then we solved this transient analysis considering the full method, that is without any approximations. Then we also solved it for semi-infinite case. So solving these equations led to some equations, and we straight away used those equations in order to find the temperature profile or the heat transfer rate for the given systems. So today we are covering these contents of week 4, whereby in the lecture sir discussed about this convective heat transfer and various modes of it, such as free convection, forced convection, and then we discussed this heat and mass transport coefficients. Then we started with this boundary layer theory, we discussed it we basically in all these first three we just give a brief overview about the topics, and in the third content, that is boundary layer, we just discuss the similarity between the momentum boundary layer, thermal boundary layer, as well as concentration boundary layer. Then in order to derive those equations for this boundary layer theory, the governing equations of this convection, we study this laminar flow and turbulent flow by the use of momentum balance. And then ultimately we also study this energy and mass balances that will lead us to this boundary layer theory that will give rise to certain equations related to the convection, that is the various correlations that govern the convection in any geometry. So yes, this introduction to convective heat transfer was very basic one, whereby we discussed about his local heat transfer rate as well as his overall heat transfer coefficient, and in order to find the overall heat transfer coefficient that is across entire geometry, we just have to integrate over entire area. Then all the other topics were related to this boundary layer theory, so we will start with that boundary layer theory in this class. So until now, if you have any doubt from the contents of earlier weeks, that is week 1, week 2, week 3, you can ask me the doubt, or else you can start with the contents of this week, that is boundary layer theory. So let's start with boundary layer flow. So here we want to study the behavior of the fluid, that is the momentum transfer, heat transfer, all the mass transfer, that is basically the concentration difference when a fluid is flowing through any surface. So let's just consider a flat plate. Okay, so this is a flat plate. Let's just assume that we are having a fluid that is going in this direction with velocity u0 and temperature T0. So at this edge, so we call it as, let's call it as the origin or the leading edge. This is x direction, this is y direction. So a boundary layer of such shape would be formed. So what it means is that if the fluid was flowing in this direction, so at the surface the fluid velocity will be almost zero. That is, it will be zero at the fluid at the surface, and as we move away from the surface, that is basically in y direction, the fluid velocity will increase, and ultimately it will become some constant, but it will keep on increasing. So if we want to draw a velocity profile, it can be shown like this. So if the original velocity was u0, so that is the maximum velocity that will be possible. So the fluid velocity will reach u0 at a certain y. So this thickness, we define it as boundary layer thickness, whereby the velocity of the fluid element becomes 99% of the original velocity. That is, u0 was the original velocity, and the thickness, whereby thickness, that is the perpendicular distance, whereby the velocity of the fluid element becomes 99%. We call it as boundary layer thickness, or until that we can say that the boundary layer is developed. So this was for momentum transfer. Similarly, for heat transfer, what will happen, let's say if the temperature of the surface was maintained as Ts, so the fluid element that is in contact with the surface will be having a temperature of Ts. Okay, so let's just consider this is my Ts, but as in how we move away from the surface, the temperature of the system or temperature of the fluid element will keep on decreasing. That is, if it was Ts, then it will eventually reach the temperature T0. So here T0 is less than Ts. Okay, so over here, that is why we can see that the temperature increases as you move closer to the surface. So again, in case of this thermal boundary layer, we can again define it as the thickness, whereby the boundary layer thickness can be defined as a thickness whereby we can achieve this 99% of the temperature difference between the surface and the actual one. So this is how we identify this boundary layer thickness. And there are these assumptions whereby we say that no slip leads to the deceleration of the fluid bracket motion. So basically at the surface, there the velocity will be zero. Similarly, the temperature gradient will be, so basically at this surface there will be conduction, and over here there will be convection. So that is what this no slip condition means. That is at boundary the velocity will be zero. Then eventually it will propagate to the faster moving layers. That is, the velocity will keep on increasing as you move away from the surface. So in case of this heat transfer, that is for conductive and convection phenomena that occurs over this flat plate or over any given surface. So at this boundary, we can write the heat conduction as Q, that is the heat flux, as Q double dash is equal to minus K of del T by del Y, where del T by del Y is the gradient at the surface, that is whereby this Y equal to 0. So this was our Y direction. So over here y is equal to 0, so we can write the heat flux as depending on this temperature gradient at y equal to 0. Similarly, the convection will occur in the fluid, so at the surface the conduction will be equal to convection, and the convection heat flux is given by this equation, that is H equal to that is Q double dash equal to H into Ts minus T infinity. So eventually at y equal to 0, in order to find the heat transfer coefficient, we can just take the ratio of both of these equations and then find the H. So that is how we find the value of any given convective heat transfer coefficient. So this formula will be very useful in solving the numericals, whereby you have to find this heat transfer coefficients. So similar to this heat transfer boundary layers, you would have studied this in mass transfers also. So there are similarity in both of those. So in case of this heat transfer, we saw that Q double dash was proportional to minus of K times del T by del Y. Similarly, in case of mass transfer, the diffusive flux from surface to fluid is given by these equations. Na is equal to minus dAB del Ca by del Y. Similarly, for convective mass transfer, so this diffusive flux is proportional to the conduction. Convective mass transfer is related to the convection due to heat transfer, the heat transfer due to convection. So again, for convection, we wrote Q double dash is equal to H times Ts minus T infinity. And in terms of mass transfer, we can write this Na double dash is equal to Hm Cas minus Ca infinity. Then in order to find the mass transfer coefficient or the convective mass transfer coefficient, we can again take the ratio of both of them and then write it in this term. So again, this heat transfer coefficient is local. That is, we had equated both this. So basically, we found that it only for some particular. We found that it for some particular area or some particular segment, but in order to find the overall heat transfer coefficient for the entire area or for entire object, we straight away have to integrate it over the area. That is basically, if a local heat transfer coefficient Hx is given, in order to find the overall heat transfer coefficient, we can just integrate it over entire area and then divide it by As in order to find the average heat transfer coefficient. Then we studied this laminar and turbulent boundary layer. That is, you can see that over the near to the leading edge, whereby the fluid near the leading edge of any solid, we can observe a laminar flow until a certain point. So over here we can see that the laminar flow is observed till a length of xc. So beyond xc we have this transition regime, whereby the flow will move from laminar to turbulent, and then ultimately the flow will become turbulent. So this is shown in this figure. So we characterize this transition from laminar to turbulent by the use of this Reynolds number, and then we see at large Reynolds number the flow will be turbulent, and at smaller Reynolds number the flow will be laminar. So this value will depend on the geometry that we are considering. So for example, for cylinder the critical Reynolds number will be different, and for flat plate the critical Reynolds number can be different. So ultimately in boundary layer we have these three regimes, that is viscous sublayer, whereby this diffusion or conduction take place, and this viscous sublayer is very close to the boundary. So over here you can see that this region is our viscous sublayer, which is very close to the boundary. And then we have a buffer, so that is an intermediate region between the turbulent region as well as this viscous sublayer. So basically you can call this as a transition regime. And then ultimately in turbulent region the main transport occurs due to this convection, and in viscous sublayer the main heat transfer occurs due to conduction. So yes, this is the same thing, but over here we have shown a plot of this distance from the leading edge with respect to various heat transfer coefficients as well as boundary layer thickness. So it is obvious that as x increases, the boundary layer thickness will increase. So from here you can see that this is our boundary layer thickness at given x. So it will keep on increasing, and in transition regime it will suddenly the rate of increase of this boundary layer thickness will be higher. So that is shown over here. Then this plot shows the variation of the heat transfer coefficient, and you can see that for the laminar flow, the heat transfer coefficient H, the convective heat transfer coefficient H, will decrease initially in this until this critical thickness, or until we achieve this transition regime. So it will decrease until that point, and in transition regime the heat transfer coefficient will suddenly increase, and eventually it will keep on decreasing in this turbulent regime. But again you can see that the heat transfer coefficient in this turbulent regime will be higher as compared to the heat transfer coefficient in the laminar flow regime. So now there are certain boundary layer approximations that we need to keep in mind while we derive these equations related to the convection over any surface. So we consider this steady state two-dimensional incompressible liquid with having constant properties, and the flow is predominantly in the x directions. Then small curvature can be present in y. So again the flow is driven by pressure gradient, and the pressure gradient is in dominant x direction. The pressure gradient is dominant in the x direction. So in order to derive these equations related to the boundary layer theory, we start with the momentum balance equations, and this equation is the energy balance. Then depending on various scenarios, we can just cancel out the terms. So we simplify those governing equations, and we get these governing equations and we solve this in order to find various temperature. To find the temperature at various length across due to this convection. So the main boundary layer approximations was this, that the gradient in the y direction are dominant over x direction. That is, the second partial derivative of u is very, very less as compared to the second partial derivative of y with respect to u. That is, del u by del y will be very high as compared to del u by del x. That is why we can write the second gradient similarly. Then again this pressure gradient inside the boundary layer is nearly same as the pressure gradient outside. So if I am having a cylinder, so if the pressure over here is P and over here is pressure is P infinity, so we assume that this pressure gradient across this entire within this cylinder is same as this pressure gradient outside the cylinder, that is P infinity minus P upon total length. The pressure gradient will be same within the cylinder also. And these approximations are true when the boundary layer is vanishingly small, that is delta upon L is very, very less than 1. So depending on, while we solve these equations, we define these various dimensionless variables such as the Reynolds number, Prandtl number and Schmidt number. These are very important dimensionless quantities that you need to keep in mind. So yes, ultimately this boundary layer theory will give us solutions, that is velocity is a function of this eta. It has nothing but the x, that is the distance from the leading edge, and the y, that is the distance in y direction, Reynolds number, and this Prandtl's number. Similarly, in case of this temperature, that is theta, it will be a function of Reynolds number as well as Prandtl's number. So in order to find the temperature across any surface at any given x within the boundary layer, we can use this Reynolds number, Prandtl's number correlation in order to find theta and velocity. So these correlations we will be studying in next week. So yes, if you have any doubt in the theory discussed for today's class, theory that was revised in today's class, you can ask me, or else we can start with solving the questions of this week. So let's start with solving the first question of the day. So the question states that in a particular application involving airflow over a heated surface, the boundary layer temperature distribution may be approximated by this given equation, where y is the distance normal to the surface and Prandtl's number. We have been given the Prandtl number, T infinity, Ts, and then we have been given this ratio, and we have been asked to find surface heat flux, 2 double dash. So just to draw a diagram of this question, so consider we are having this heated surface, and we have been given airflow is occurring. So if this is the direction of the airflow, so the velocity of the air is u infinity. Then we have been given that the boundary layer temperature distribution may be approximated by the given equation. So let's just consider this as our boundary layer, and within this boundary layer we have been given this temperature distribution. Let me just see. Okay, so over here T infinity is 152, whereas the temperature of the surface is 27 degrees Celsius. So we will be seeing such a kind of temperature profile. So this T infinity is 152 degrees Celsius. The temperature of surface is 27 degrees Celsius. And within this we have been given this temperature distribution given by this equation, that is theta is equal to 1 minus exponential of Prandtl number mu infinity v by y. And ultimately we have been asked to find the surface heat flux, that is Q double dash. For surface heat flux you need to find the heat flux at this point. So ultimately we studied that at the surface the heat conduction will be equal to heat convection. So you can use those equations in order to find Q double dash. So I will give you around, let's say, 10 minutes. So these are fairly simple questions. I'll give you around 5 minutes to solve the questions, and then we can discuss the solutions. So we will start to solve this question. So yes, as discussed in the diagram, we have this surface and the fluid or air is flowing through, and then the temperature difference. So there is this temperature profile. So this temperature profile has been given by this equation. T minus Ts is equal to T infinity minus Ts 1 minus exponential of minus of PR U infinity Y by V. And then we had been asked to find Q double dash. So at surface, we can write the heat balance as basically the heat flux due to conduction and heat flux due to convection, both will be equal. So basically, if the temperature of the surface is Ts and the ambient air is T infinity, or else, and the ambient air is T infinity, so we can write that as heat transfer coefficient minus of Ts minus T infinity, or due to the convection can be minus of K del T by del Y at Y equal to 0. This is we can write if we had to consider this entire, but we only need to consider this neighborhood since we have been given this. We have to find the surface heat flux. So over here it will be T. So you can use either this equation or equate this to this equation in order to find the heat flux. But in the question we haven't been given the convective heat transfer coefficient, so we will use this conductive heat transfer. So that is Q double dash is equal to minus of K del T by del Y at Y equal to 0. So we need to find this temperature gradient at Y equal to 0. So we will differentiate this equation with respect to Y and put the value of Y as equal to 0. So this equation we need to differentiate. So it will become del T by del Y minus 0. This will be a constant, T infinity minus Ts upon 0 minus of exponential of entire this term, and then in multiplication we will be having minus of PR V infinity mu. So yes, this minus will become plus, and if we put the value of Y equal to 0, this exponential, the coefficient, the power of this exponent will become 0, so ultimately this will become 1. So we are left with del T by del Y is equal to T infinity minus Ts into PR U infinity upon mu. So we replace this temperature gradient in this equation in order to find Q double dash as, so it will become minus of K times T infinity minus Ts one Prandtl number mu naught into V. Now we just need to replace the values. So the value of thermal conductivity is given as 0.0263. Then T infinity and Ts are given as 152 and 127. So 152 minus what? 152 minus 27 will be 125. Then Prandtl's number is 0.7, and then we have been given this ratio as, I think, 5,000. So you can try solving this and you will get an answer of 0.0263 into 125 into 0.7 into 5,000. So it will come around 11506. So over here we had this minus of 11506. So our answer is option B. Yes, so the final answer is 11506. That was option B. So now let's move on to the second question. So the second question says that a flat plate is of planar dimensions 1 meter into 0.75 meter. For parallel laminar flow over the plate in two cases. In case 1, flow is in short direction, and in case 2, flow is in the long direction. So what is the ratio of average heat transfer coefficient for the two different flow orientation? Which orientation will result in a larger transfer rate? That is, heat transfer rate will be equal in both the orientation. Heat transfer rate will be larger when the flow is oriented in the short direction. Heat transfer rate will be smaller when the flow is oriented in the short direction, or the heat transfer rate will be double when the flow is oriented in the short direction. So yes, for this given boundary layer, the heat transfer coefficient is related to the distance from the leading edges. It is straight away proportional to x raised to minus half. So this is a local heat transfer coefficient Hx, and in the question we have been asked to find the correlation between the average heat transfer coefficient for different scenarios, whereby in first case the length is 0.75 meter and in the second case the length is 1 meter. So what you need to do in this question is, in order to find the average heat transfer coefficient over the entire length or over the entire plate, you just need to integrate this local heat transfer coefficient over the entire length. That is, HL will be 1 upon L integration of 0 to L Hx dx. So you can replace these values over here, and then you can find the correlations between both of this length. So you can try solving these questions. So we will discuss this question in a couple of minutes. If you have any doubt, you can ask me and we can address your doubts. So let's look at the solution of this question. Hello. Okay. So yes, in this question we were given such a diagram. So this is a solid surface. This was our boundary layer theory, and the thermal boundary layer, for thermal boundary layer we were given this Hx is proportional to x raised to minus half, or we were given this Hx is equal to c x raised to minus half. Then we have to find the average heat transfer coefficient. So as discussed, in order to find the average heat transfer coefficient, that is h bar L, we have to integrate this over the entire length. So that is nothing but integration from 0 to L hx dx. We need to replace this over here, and it will become c will be constant 0 t to L minus of x half upon dx. So if we just integrate it, it will become x raised to minus half plus half upon 1 by 2 and c upon L, and the limits are from 0 to L. So it is becoming c upon L root of x, and we put the value of L minus of 0 upon 1 half, that will become basically 2. So this will become 2 into L raised c into L raised to minus half. That is the overall heat transfer coefficient. We can say that it is proportional to L raised to minus half. That is for both the scenarios. The ratio of average heat transfer coefficient will be, let's say, HL1 upon HL2. So it will be nothing but L2 by L1 raised to half, that is under root of L2 by L1. So this is the ratio that had been asked. The second question was, which orientation will result in a larger heat transfer rate? That is, heat transfer rate will be equal. So in which orientation the heat transfer will result in a larger heat transfer rate? So basically the heat transfer rate is proportional to, the value of the average heat transfer coefficient. So, and the average heat transfer coefficient will be higher when the length is lesser. So from here you can see that it is inversely proportional to the square root of length. So if the length is less, the heat transfer coefficient will be higher, due to which the heat transfer rate will be higher. So we can say that in the short direction, the heat transfer rate will be higher. That is, the heat transfer rate will be larger when the flow is oriented in the short direction. That is, option B is the correct one. So I hope the solution of this question is clear. Now let's move on to the third question. So yes, this was the solution. So you can try reading this third question, and I will explain it once we solve it. So in this question we have been given that experiments have shown that the transition from laminar to turbulent conditions for flow normal to the axis of long cylinder occurs at critical Reynolds number of this. So the first thing we have been given this critical Reynolds number for the cylinder, that is 2 into 10 raised to 5. So this means that if the Reynolds number is less than this, there will be a laminar flow. Then moreover, the transition from incompressible to compressible flow occurs after a critical Mach number of this 0.3. So we have been given this Mach number critical as 0.3. Then for an air of pressure 1 atm and these other parameters and temperature of 27 degrees Celsius, we have been asked to determine the critical diameter DC, below which, if the flow is turbulent and compressibility effects are likely to be important, assuming the air behaves as an ideal gas. So for these scenarios, we have to find this critical cylinder diameter DC, for which the turbulent and compressibility effects are likely to be important. That is, at this critical Reynolds number, we have to find the cylinder diameter DC. So you just need to remember that Reynolds number is given as rho v velocity d upon mu, and this velocity you can find from the Mach number. So then putting the value of Reynolds number in the other related parameters, you can find this critical diameter DC. So just to give you an idea, I don't think we have so we have defined this Mach number as over here. So Mach number is the flow velocity v upon local speed of sound. You can call it as c. So from over here you can get the value of v. Just put that over here and you can try solving it. And consider that this is an ideal gas. So this will be useful in order to find the density rho. Just try solving it or try solving the question on your own. We can solve it later. So yes, let's try to solve this question. So yes, the first thing we had been given. So yes, in this question we had to find this critical Reynolds number, critical diameter of the cylinder, that is DC, and we discussed that we were given this critical Reynolds number, that is rho v dc upon mu. So from that we can get the diameter as Reynolds number into mu upon rho into velocity. Reynolds number we have to use 2 into 10 raised to 5. Viscosity, if you require, you can use over here. Density we don't know over here. So for this give, you can write this density is equal to P is equal to rho RT, that is rho is equal to P upon RT. We can use this equation since the value of gas constant we are taking in joule per kg Kelvin. So this you can use over here. So temperature we have R, we have pressure we have to take as 1 atm, but we have to consider it in terms of bar, that is 101325 Pascal. So this is the pressure P. So from here you can get the density. So the other thing remaining is to find the velocity. So for velocity we need to use this Mach number. So Mach number is given as flow velocity past the boundary, that is v, upon the local speed, that is c. The local speed is given by this equation under root of gamma RT. So yes, from here the velocity will be Mach number into gamma RT. So let's just put all those formulas in this equation. So you will be getting diameter is equal to Reynolds number into mu upon rho is P into RT, and Mach number is upon gamma RT. So the diameter in this scenario will become Reynolds number upon Mach into mu upon pressure. Then we will be having this root of RT upon gamma. So this is the formula for critical diameter. Then you need to put all those values. So the Reynolds number is I think 2 into 10 raised to 5. Mu is 184.6 into 10 raised to minus 7 upon Mach number is 0.3. Pressure in Newton meter square is 101325 into under root of R is 287. Temperature is 27 degrees Celsius, that is 300 Kelvin upon gamma. So gamma is 1.399. So as you can try simplifying this, try to calculate it, and the value of diameter will come around 30 mm. That is option A is the correct one over here. This is the correct answer, 30 mm. So So let's move on to the fourth question. So this is related to the related to mass transfer. So whereby we have been given that the rate at which water is lost because of evaporation from the surface of a water body may be determined by measuring the surface recession rate. Consider a summer day for which temperature of both water and the ambient air is 305 Kelvin and the relative humidity of the air is 40%. If the surface recession rate is known to be 0.1 mm per hour, what is the rate at which mass is lost because of evaporation per unit area, and then what is the convective mass transfer coefficient? So yes, for this mass transfer we saw this equation that is very similar to the heat transfer equations. So yes, we studied this equation. So over here we have been asked to find this HM. So yes, we will use that. Okay. So for calculating that, we can write the equation as NA is equal to HM. HM into, let's say, constant between the concentration difference. Okay, Ca1 minus Ca2. That you can alternatively write this in terms of this mass flux, because we have been asked to find the rate at which the mass is lost as. So mass flux due to evaporation will be equal to HM into density of the saturated air. Then the evaporation is occurring from water. So the concentration of the, so over here there will be 100% water, so the concentration is 1, and over here we have this relative humidity of 40%, so it will be 0.4, but we don't have this HM, so that is what we have been asked to find in the second question. So HM we have to find, but for that we need to find this rate at which the mass is lost. So for that you can simply write this conservation species across this control volume of water, that is whatever the mass is going from the liquid is ultimately getting evaporated. So in other way you can write this as minus of mass flux into A is equal to d by dt upon the mass that is getting evaporated. So this is mass flux rate into area, and basically this is the flow rate. Okay, m double dot A into area. So mass you can write it in terms of density into volume, rho into V. Density is constant, so you can just take this out. So over here the change, we are calculating the change of the mass in the water, so we will consider the density of fluid. And the change in the volume, so volume is nothing but area times of the head, so h is the A times h, and h is the level of the height. That will change, but area will remain constant, so we can write this as A upon dH upon dt. So this will be equal to m double s into A. So this A will get cancelled, and we have been asked to find the mass transfer rate, basically this term. So dH upon dt is, I think, the recession rate that is given as 0.1. So you can just write this as rho f into 0.1. So you can just replace this rho f into 0.1 over here and get the value of HM. So I have more or less solved this question for you. You just need to do the calculation and just give me the answer, and then we can move on to the next question. So if you try to put this value of rho f into 1, so you will be getting the value of hm as rho f into 0.1 upon rho saturated into 1 minus of 0.4 is 0.6. Then we will just replace all those values. So you can try replacing all those values, and the final answer of the mass rate will be 2.76, and the convection mass transfer coefficient will come around 1.37 to 10 raised to minus 3. So you can try solving this on your end and you will get this answer. This is the solution. So now let's move on to question number 5. So question number 5 states that if a laminar flow is induced on the surface of a disk due to rotation about its axis, the local convection coefficient is known to be constant, that is h equal to c, and it is independent, it is independent of radius. So consider conditions for which a disk of radius r not equal to 100 mm is rotating in stagnant air at T infinity equal to 20 degrees Celsius, and the value of c is equal to 20 watt per meter square Kelvin is maintained. If an embedded electrical heater maintains a surface temperature of Ts equal to 50 degrees Celsius, what is the local heat flux at the top surface of the disk, and what is the total electric power requirement? So the first thing, in the first question, we have been asked to find Q double dash, and in the second question, we have been asked to find the power, that is nothing but Q. So whatever answer you get from over here, you just need to multiply it by area in order to find the power. So try solving it on your own. After this, we will take one more question and then we can wrap up today's session. Okay, so I will just share the solution with you. So as discussed in the first question, we have to find Q double dash. So Q double dash, that is the heat transfer flux. The heat flux is nothing but H times T s minus T infinity. Since the local convection coefficient is independent of radius, for the overall heat it will be the local heat transfer coefficient will be same as the overall heat transfer coefficient. You can verify the same as by integrating it from 0 to r dr, and hr is nothing but constant, and upon 1 upon r. So this will become c by r into r, so it will be c. So the overall heat transfer coefficient will be c, so it will become Ts minus T infinity. The value of c is given as 20, value of Ts is 50, and T infinity is 20. So it will become 20 into 50 minus 20, so it will become 600. Similarly, power, you can just multiply it by the area. So the area for this case is pi r square, so because the heat flux is occurring in this direction. So you can just multiply the 600 into pi into r naught square, and you can get the power as around 18.9 watt. So the local heat flux, we calculated it as 600, and the total electric power requirement is 18.9 watt. So yes, this was the solution. Now let's move on to the last question, that is question number 6. So over here we have been given that parallel flow of atmospheric air over a flat plate of length L equal to 3 meter is disrupted by an array of stationary rods placed in a flow path over the plate. Laboratory measurements of the local convection coefficient at the surface of the plate are made for a prescribed value of V, and Ts is greater than T infinity. The results are correlated by an expression of the form Hx equal to, given by this quadratic equation, where Hx has the unit of watt per meter square Kelvin and x is in meters. Evaluate the average convection coefficient for entire plate and the ratio h bar L upon L for at the trailing edge. So we have to find this average convection coefficient h bar L for the entire plate and this ratio at the trailing edge. Trailing edge means x equal to L. So again, for this given local heat transfer coefficient, you have been asked to find h bar L, that's the overall heat transfer coefficient, and then this ratio at the trailing edge. So we have solved this similar question. You can try solving it on your own, and I will just discuss the solution in 5 minutes. So let's discuss the solution of this question. So we have been asked to find the average coefficient, that is h bar L, and then this particular ratio, that is h bar L upon HL at the trading edge. So this h bar L, we studied it as 1 upon L 0 to L hx dx. So this we can just put over here, and HL is nothing but hx at x equal to L. So the first thing we need to find is this integral. So it will be 1 upon L integration of 0 to L. Hx is given by this polynomial equation, and if you integrate it, integration of 0.7 will be 0.7x plus 13.6 x squared by 2 minus of 3.4 x cubed by 3, the integration from 0 to L. So this will become HL. So it will become 0.7 plus 6.8 L minus of 1.13 L square. So this is our equation for HL, average HL. So at length we have been given as 3 meters. So h bar L, you can just put value of 3 in this equation and you will get the value of h bar L as 10.9 watt per meter square Kelvin. So that is our first answer that has been asked. So the second question, we have been asked to find the ratio of h bar L upon HL. So in order to find HL, you need to put the value of L equal to 3 in this equation, local. So if you just put it, you will get 0.7 plus 13.6 into 3 minus of 3.4 into 9. So this will also come around as 10.9. So the ratio of both of this will be 1. So for this particular question, the ratio of the average convection coefficient for the entire plate upon the value of this local heat transfer coefficient at the trailing edge will be 1. So that is our final answer. So the solution to this question is also shown over here. The ratio will be 1. So that was all for today's class. We solved this question, 6 questions related to this, mostly related to this convection, whereby we had to find this average convection coefficient for different scenarios. And then there were these few questions related to this calculation of the heat flux. So yes, if you have any doubt, you can ask me. I will be here for a couple of minutes, or else we can end today's session. Yes, this was question number 6. So okay, if you don't have any doubts, let's wrap today's session. Thank you everyone for joining.